So basically, we would like to understand what's inside this teachable AI or teachable machine model and how it's been trained. And let's have a closer look into them. So when we talk about models, here we will see a couple of them, like how they could be structured. Like in the beginning, we defined a very simple model, right? So we had just like one neuron and two inputs. So that's like the simplest form you can have. And obviously, you can add a lot of nodes with each other. You can sum up them with each other. You can also do like things that you have certain layers, and then, for example, they just are connected with one instead of all of them. This one, for example, here is a so-called fully connected network that's been widely used for handwritten digits. It seems to be quite solid network structure. But then, of course, we also have different forms like this one, for example, which is so-called mobile network. This one was defined for smartphones, so it's quite fast and not so big, as the smartphones don't have such a huge CPUs, but still it performs quite well for object detections. Like here on the top right, we have a so-called, that's like a broader topic of convolutional neural networks. And this here, for example, on the bottom right is a so-called inception network, which was defined by Google. Also performs very well on object detections. And like all these different structures, what we see here, let's say like this, here you see this kind of blue patterns. They are, you can kind of say like also neurons. It's just another representation of it. And all of these different network models had been designed over time, and of course, like in different research labs, they came up with these structures to say like, okay, this seems to be the best form of, or the best shape of a network to, for example, identify objects in images. When we talk about large language models, I'm not sure about how they are structured. I can just show you like how it's been made with images here for the moment. But I can imagine that for large language models, they kind of follow same structures of these kind of models. And today we will have a look into two of them. So basically we will have a look at this one here on the top. This is like a ConvNet, it's called, where we broadly used. Seems to be quite okay-ish for object detection, but it's quite heavy. We will have a look at it. And then we will also have a look at this mobile net, as this is running on our smartphones, for example. And let's see, maybe next one. Well, let's see if we have the time. But let's have a look. So this is the convolutional network, or ConvNet. And what we can see here is exactly what we want, or what we also kind of have seen in the teachable machine, is that we take an image. It somehow gets analyzed in the network, and then here in the end it can be split into separate categories, and then here we see the output would be something like, okay, I see a car, I see what else, a truck or a van or something like this, or bicycle. Depends on the categories we are training on it. And in the network itself, we see the different stages. There's, for example, convolutional, ReLU, pooling, and then it's the same, doing the same over again. Then we see here like there's a flattened, fully connected thing. So we see that there are also, maybe going back here, there is basically a combination between this step, and then in the end we have a fully connected network, meaning that all the neurons are connected with each other. And so the question is like, how is that implemented into code, and how is that represented also in code language? So therefore, let's have a look into onto the web page, and we open the Google Colabs notebook. So we go onto our course web page, and we will launch this one, which is called Launch ConvNet Dogs and Cats Classifier. So we're gonna go in here. I'm gonna quickly close all the other tabs here. Okay, alrighty, so everybody's here. I guess you remember, right? We had this open already last time. I'm gonna show you or guide you quickly through again. So first of all, unfortunately, we need again like a Google account to sign in. It would ask you once you open it. And so this is our code, our program that again runs on a server farm on Google, so no resources we have to spend here on our machines. And we basically have the code here separated into so-called certain cells, which we can execute one by one. But before that, we would like to have it as fast as possible, and therefore we have to select the resources we would like to use it with. And here on the right side, you see there it says connection, and there's this arrow button down. And when you go to Google Cloud Runtime Connection, sorry, this is the wrong one. We have to go to, maybe is it? Yes, it's runtime type change, this one. Again, I'm gonna go there. So it's like on the right side, arrow button down, and then it's the second from the top. And here you can define the GPUs you would like to run the code on in the data center. I pay for that, or I paid for a certain amount of credits, so I'm not sure how it will look like on your end or what kind of types you will get here. For sure you don't want to have the CPU because this is the slowest way to run the code. So you would like to have something that says in the end GPU or TPU. I would say maybe you're gonna see this one, the T4 GPU. So you can select this one. I'm gonna take this one. Why not? I'm gonna take this one, it's fine. So do you see the option, this one? Yeah, T4. Alrighty, and then we go to save. Also, you should have Python 3 up there, but it's automatically selected. And then here on the top right, it tries to connect you to the T4, and it always depends on if they have some free resources or not. If they do, they will connect you with it. If not, they probably will say like, okay, I'm not able to connect you, and then you go back to the CPU. We will learn it by running it. But again, let's have a look into the code. So this example is basically the same what we did in the Teachable Machine platform, but just translated into code and what's running there in the background. So we have everything here written in Python, which is like the most common language in machine learning. And I mean, of course, right, we will not learn Python here in this course, so I can kind of just like tell you what these kind of functions do. And a lot of stuff is already automized. So these are basically libraries on libraries on libraries. So it's really like a very abstract form of the code, and a lot of stuff is going there under the hood. So I'm gonna quickly show you what you see. So basically the first block of code here is kind of just installing some libraries. For example, the one important thing here is so-called TensorFlow. So like this is the most widely used library for machine learning. A lot of researchers use it these days. It's kind of a very easy way to work with machine learnings and models, and basically gets been installed here. So this is this part. It also installs some useful libraries, like for example unzipping files. And NumPy is a very known thing to use with mathematical operations, but we don't have to pay attention too much on this one. So maybe this part is interesting. So here I basically download the data set from the web page that I showed you before. So this code here will automatically download this one for us, and also it will unzip the file and puts it on our Google Drive folder. So that's a very handy function, so we don't have to go to the web page, download it manually and upload it there. So basically this piece of code here will already do that for us. And once we do that, then you will find it here on the left side, which is now empty. Once I execute this code, like here on the left side, you see the folder. That's basically our Google Drive folder. There's already some sample data. It comes by default. But once I run this one here, let's see. So let's click on this one on the top left. You see it basically, yeah, on my end, basically it was already installed, so it doesn't do that again. The bigger part is this TensorFlow version. This downloads it, and here we see already it downloads the training data. And once that's done, you should see exactly the same folder structure as we have seen before when we downloaded it manually. And then I can go into training, cats, and then I will see all the images. I can also download them here individually if I like. Somewhere, yes, here. And of course I can always also upload images into the Google Drive and then use them into my code, which is quite handy. Saying this, basically this notebook just exists temporarily, like when you basically close it, then you have to do everything from scratch again. What you can do is, if you would like to keep it or save it, you can go to the top left to Files, and then you can go to Save. So this will make a local copy onto your Google Drive whenever you want to use it later. Okay, I close this one. So this one is green, so all good. So we can go on to the next cell of code. So basically here, this is the cell where we prepare our data set for training. It's literally the same thing what we did in a teachable machine. So we're gonna say like, okay, look, we have a training data set and we have a validation data set. Here we define the path where the code will find these two data sets. This is basically, it's called OS path join, and then we have the base here. The base here is basically like this one, the root path, and then it just adds the train or validation path at the end, so that the code knows where to find the two different data sets. Then we have here a parameter which is called batch size. I will come to this later. And here, this is quite important. Here we're gonna tell the code to resize every image to 150 by 150 pixels, because remember, basically the original file size is 512 by 512, as I remember. And what we want in our code is, because it's way too big, we want to reduce it. We would like to scale it down to 150 by 150. So that's an interesting information. So that means that the neural network or the model is actually training the algorithm on much smaller data, or that resolution-wise on much smaller data. And this gives us already an interesting information about certain tactics to manipulate data as well, as we know that it will shrink it down, but that's something I'm going to show you later. But saying this, it seems to be that neural networks, they don't need crazy big images to be trained on. They can actually already, and it turns out it's even also more efficient to use smaller images than bigger ones, as it's much faster, because if you have bigger images, that will take much longer than to train. So then here we print, this is just like an output. Basically we print how many training data we have, how much validation data we have. It's just like a nice debugging scene. And then let's run it, so we can validate that the code is also now ready to work with our training and validation data set. So I'm gonna run this code, and you can see here that it found 2000 images in the training data set with 2 classes, which is correct, dogs and cats, and the same is also here true for the validation data set. So we have in total 500, right? So we have 500 cats, 500 dog images per class. And the reason why it found 2 classes is literally here in the code is just by the folders. So basically, when we go in here, we have these 2 folders, and this is how the code knows, okay, it looks like you have 2 classes you would like to look at. We can easily also add another folder and call it, I don't know, rabbit, and here also here, and then put some rabbit images in it, and then we would have like 3 classes. So this code is kind of smart enough to identify just by the folder structure how many classes we would like to train on. Alrighty, and then we go on and have a look a bit deeper into this network. So what you can see here on the left is the original image, and you can see that suddenly the image gets reduced and gets smaller and smaller by its resolution. That's basically representation what we see here in the first part of the network. And the way how they reduce it is not just by scaling it down resolution-wise. Basically, what networks or this convolutional neural networks, what they do is they use as this kind of method which are so-called kernels or filters. We basically know them already. The same technique is also being used, for example, in Photoshop or in any other image manipulation software to add, for example, filters like blur, edge detection, and things like this. And the way how they work is they basically are some kind of filter that goes over the image, pixel by pixel, and then they count together with a so-called dot product the average amount of those pixels and print them or transform them into a new image. And by doing so, it's basically the idea is here that, again, we don't need a crazy resolution image. We would like to reduce it, but still keep the core information of the image. So we take this kind of filter, scan, go over the image, and always take the average, let's say like this, of the pixels and print them into the new image, which is then kind of reduced. And we do that over and over again until we have maybe, let's say, an image that's just like 32 pixels, but 32 pixels is quite small, but still keep the core information. So this is like a technique called kernel filtering, very commonly used in analyzing images. And I mean, I'm just gonna show you, don't have to really 100% understand it. I just would like to let you know, or would like to give you a bit like a knowledge, like how it can be, you know, that the resolutions are getting so small, but the network still keeps the information. And so this is the kernel thing, and then there's another technique in the end, like here is another kind of kernel filter that goes over it and always keeps just the highest number in this block of pixels that's analyzing it. So that's called max pooling, and we see that in a second here in our code, so that you get a better understanding what the code is doing with this animation here. But again, more like a visual presentation, let's have a look at the code. So basically here, this is literally our network, and that's all how a neural network looks like. And it's super simple structure, like from the code, where it's not crazy amount of code, it's literally just a representation. So basically the first part is, so it turned out that when we input some images into a network, researchers said, like, actually to make the network much more solid and more stable, we can also manipulate the data set in itself by rotating it and shifting it slightly and mirroring it during the training process. So what this piece of code is doing is actually it takes the image, it takes it originally into the network, but then for the next training phase, it adds certain rotations on it and shifts like a little bit, so that the training data set gets much more variations and more and more stable, so to say. So that's more like the training data set. But here the network itself. So again, we take an input of 150 by 150 pixels. Again, we have the 3 different color layers, as we said before. And then here we define Okay, here we scaled down the pixel space, that's fine, but here basically we define the first layer of the input, of the network. This is so-called a concat 2D, and it reduces the image to 23 pixels or 23 filters and to 3 different color channels. So this part of the code here basically is exactly this layer. And we can do then this called thing here, which is called max pooling again. So this is like this kernel. So we say like, okay, run the first part, so run this thing. And once you have minus values, please always take positive values. So it's this called ReLU. And once you have positive values, then please take the highest value out of it and reduce it to another image here. All I want to say is like this part here can be endless. So basically you can easily also just copy this one, and then you can basically copy this over and place it in here, for example. And you can add as much as many layers as you like to into the code, and there's literally no no limit of how many layers you can add. Oh, that was too much. And that was the whole set. So there is this thing of when you add more layers, it doesn't necessarily mean that your code gets more accurate or it gets better, but it can be that if you add certain techniques and certain layers, like the ones we see here, that maybe certain features are getting much better detected than other ones. And this is also the part where the research takes quite a lot of energy into, like what is the exact combination of layers that we need to get the result we want. And this needs also testing, and that's also where a lot of energy and resources are into place in data centers to find that out. I mean, over time, as these networks are, almost, a couple of years old now, somehow it seems to be like object detection, this kind of structure, what we see here, which is basically this part of the code, is already quite solid, and I think there's not so much to improve, but still it's not saying that this is the best network for your specific purpose. But again, easy as it is, let's just execute it, and we're gonna say here when we run it, this is our network, and this is how I would like to design the network for the moment. So let's keep it as it is. So this part is basically, like here I can quickly go into, like this I showed you, right? This part here is this part of the network. And then we have here the other part which looks a bit different, like we see fully connected neurons, and then here the output is the labels or the categories. And that's basically this part here. So here we do like a so-called fully connected network, and we scale it up, we flatten everything, and then we just say like, okay, please just do a categorization between two labels. Let's take it as it is, that's fine, because again, this network structure for labeling seems to be the best so far. I would like to quickly raise your attention to this one, because maybe you have heard about that neural network or machine learning is about to find the deepest valley of certain structures. Maybe remember like when we had like these biases and weights and we were trying to find out the right numbering there and combinations. That's exactly what this is represented here. So when people say like, neural network is kind of finding the deepest valley in a certain algorithm, basically what they're going to try to say is like we need to figure out the correct weights and biases so that we find this line that separates the data with the less wrong decisions. That's how they say it. And for this finding, or this kind of finding the right numbers, there are two different functions. There is the so-called loss function, which is a commonly used term in machine learning. And I use this kind of example here, which basically means, like, imagine you playing a basketball and you try to throw the basketball into a hoop, and every time you miss it, like you throw it to the left or to the right. So the loss function is basically kind of measuring, that tries to measure how far you're away to throw the basketball into the hoop. It's basically like a measuring tool. That's the loss function. So this is like basically how far you are away from the deepest valley to find the best numbers, the best weights and biases. And then we have another parameter which is called the optimizer. And the optimizer is basically a trainer that tells you, like, hey, look, next time you should maybe go a bit more to the right, or next time you should more to the left to find the best angle here and throw the ball into the hoop. And the loss and the optimizer are basically defined down below. I think here, yes. So that's where we define this and say, like, okay, I would like to have, for my training, I would like to have this optimizer. It could be also something else. There's, for example, one that's called Adam optimizer. There are a lot of different explanations for this. And here we say, like, okay, I would like to find a network. Here I structure it, and once I run this cell of code, it kind of gives me back the again structure of the network, and it also tells me the amount of parameters my network has for the moment. So here, for example, we see, like, this network has 90 million parameters now, meaning that we have 90 million weights and biases in the network. I don't know, maybe we can quickly have a look, like Gemini Flask parameters total. Let's see how much it has. So, for example, Gemini 3 or Pro has about 6 to 7 trillion parameters in our network, meaning, right, parameters means those are the weights and the biases, what we had before. So our network has 19 million. So of course we are far away from what this kind of top-notch models have. But just to give you an idea of what we are training on, sometimes you hear in public debates, like, this model has this kind of amount of parameters, and that's what they are talking about. Alrighty, and so, okay, we run this one, we define it, we say, like, okay, now that's our solid structure, that's our model, and then we have these other two parameters here, and these are the so-called hyperparameters, which we can set during the training. And there's one which is called batch size, and the one is called epoch. Batch size we had already up here somewhere, I think in the beginning, and it was set to 32. And I wonder if it takes that into account, but let's see. So basically the batch size means that we have 1,000 images in our algorithm that we can train on. Unfortunately, the machines are not so strong to load 1,000 images at once into the algorithm. So we have to split the data set into smaller pieces and then to run it over and over again. And what we do is here we say, like, okay, please split the data set of this 1,000 images into smaller bits. Actually, it's set like 32 images per training phase, and then run all over them. And how often we run it is defined by the epoch, which is this one. And here we say, like, okay, I want that you run over my training set defined by the amount of epochs, which would be here in our example 15. So what we say is, like, please run over the data set 15 times And after 15 times, I hope that you are good enough to do like a good prediction. And this is actually also what takes a lot of effort in it. Like to say, okay, maybe a 20 is enough, we need 20, or maybe 10 is enough. So this number here, the epoch, is quite powerful with regards to how long the network will be trained on. But let's run it. So basically, this one is now the training phase, the history, and when we run this, execute this cell, it will start to train our network, and this will take a bit of time, depending on our graphic card we selected, or like the resources we selected. But it seems to be it's kind of quite fast here for me right now. So basically, again, each epoch shows the network, the whole data set. So what we do is basically we show 15,000 images. And remember, we had here also this one thing in it where we add some kind of random rotations and shifting, mirroring into the training data set. So every time we run through a different epoch, the data set will be slightly different because the images got slightly rotated or shifted. Alrighty, so for me this is already done, the training process, quite fast. Here I can also print the metrics. That's a good debugging window so that I can see how good the training performed. And I can already see that here we have quite some gaps and it didn't perform that well. So basically what we want is like a very nice flattened curve so that the training, basically this one, goes from 0 all the way up to 1, and the blue line and the orange line are basically kind of simultaneously. So the blue line is the training data set, and the orange line is the accuracy training data set. Actually, the orange line is more important for us to see. So this should be, the orange line should be quite close to 1 or even flat up there. And we can see also here that should be, this is the loss function, so this should be goes to 0. As you remember, right, this is basically the loss thing. It shows try to find the lowest value here in the curve. And we can see we have some spikes, and it's not such a, so the training process was not such that I cannot tell you, or I would say like probably the network we have here right now is probably not the best, but let's see. We can run it now. So I'm gonna go now execute the next cell, and this cell now basically asks us for uploading an image where we can now this run against the network and detect if it's working or not, or how good it's working. So I'm gonna upload a random image here. In this sense, it would be a cat. And now it's analyzing it, and it's predicting this one as a dog. So it seems to be that this network or this network structure is not good enough. We can run this cell again and upload another one. Maybe I take another cat. Let's see. Analyzing it. Still predicting it as a dog, and you can see here that the confidence score of the network is 50%. So it's kind of, really the network really doesn't know 100%. Like it's kind of undecided here, 50-50 if it's like a dog and a cat, and it made like in the last 0.483% made it to decide that it's a dog. So this network seems to be not perform so well. So now we have to go back basically and have to change a certain parameters. For example, we could play around with the epoch size here and maybe set it up to 20. So basically we will run it a couple of more rounds more. And so I'm gonna run this again. So this could be one parameter we have to fine tune. Again, this is a so-called hyperparameter, or maybe the whole network model architecture is not the right one for our purpose. So maybe this structure here is not well made to identify cats and dogs. So we might also could think about to change the whole model structure. So right, this one is done. I'm gonna run the analyzer again, the debug scene. Okay, it goes even, I don't know, let's see, maybe crazier. I can see that the training data performs a bit better. I mean, still it doesn't go all the way down to 0 here for the loss function. This one should actually, the blue line should also go up to 1 here. But let's see, we can have a look. So we're gonna execute this one. I'm gonna upload another cat image. Well, I mean, at least it kind of has an 84 confidence score that this is a cat, so it seems to be a bit better. Let's try it against another cat image. Well, unfortunately, still a dog, but 50%, so 50-50. Let's see how it goes with a dog image. Validation, go to dogs, and all right. So it seems to be that there is something in this architecture, or like in this whole training process, and I mean, this already tells us this one, not so nice defined. So it might be again either the hyperparameter of epoch, or it could be also, when we go all the way up here, the batch size that we have to change, and that's like one of the things that that always needs to be figured out when you train networks. Like, what's the best parameter here? There's also another hyperparameter which we call the learning rate. It's defined here. This one. This is like a super small number. Basically, this LE minus 4 means it's something like 0.0004, something like this. So maybe this number could be also too high. So that could be also one indicator. But all I wanted to say is, like, this is what it means if you train a neural network, is to play around with these parameters and to figure out the right settings to get the result then in the end you want. And this is also like very time consuming, and it takes a lot of resources, because the problem is here that you have to run it once. After you see the result, then you can fine tune or tweak the parameters. But I know that this model architecture is not the right one. It's not the best one for our purpose. And therefore, we quickly go over to the second example here, and we're gonna have a look into a different modeling infrastructure, which is this one. It's called mobile net. So we're gonna open this one. And alrighty, so I go over here. So this is the cats and dogs example mobile net version 2, and we see the same code. It's exactly as it was before. So we can like here, I'm gonna close it, open this one. It's empty for the moment, and I run the first. Also make sure that we also select here the right runtime, or like the runtime type. So I go in there. I'm gonna take the TP. So now it says like I'm already connected with another notebook. So I have to kick out maybe I can close this one. I might be still connected, so you can go to, which one was it? Let's see. This one. Okay, runtime, yeah, save. And then let's execute the first cell here in the code. So this does exactly the same. It installs TensorFlow, it downloads our training data set. Then we see it here on the left, already downloaded. Then we have the same scaling factor here. We also scale down the images to 150 by 150. We set the same batch size, and we define the training and validation data set in here. So I run this one. So that found all the files and the classes. And then here we have this randomizing structure in a different shape. So we say like, okay, for every round we'd like to have slightly rotations and shifts, and zoom also interesting. So it also zooms into the image and shows like a bigger or like a zoomed in version of the original image. So shuffle with the data set. And this one now is basically the new model that we define, which I know performs much better than the other one before. Let me show you. We are here. So this is the mobile net. It looks a bit similar to the one before. The only part that's not in here is the last part basically has changed. Like in the one before, we have seen that there are much more layers here in the background, fully connected layers. And we get rid of them and just have one flattened layer, like one big layer in the end, that then in the end spits out the categories. And I think that's probably the only difference compared to the other model before. But let's have a look. So basically, we also have the same here. We see that there's also an optimizer. We have the same optimizer than we had before. Here in this example, we also use the Adam optimizer. Here we can see the learning rate written out. So this is the 0.001. And the loss function is called cross entropy. But anyway, we're gonna just define this one. Now it also prints out the structure, and here you can see we have much less parameters now in our model. So sounds first of all a bit different, but actually it seems to be that less parameters might perform better than the 90 million parameters we had before. And let's do the training. And here I also have an epoch size of 10. That's also different, so I have less training rounds. So this seems to be a bit slower because I might have to, no, fine. Yeah, don't over it. And we can also see here in lifetime actually at what stage the network is right now and how the loss goes down and the accuracy goes up. And again, we want that the loss goes almost to 0. And we would like that the accuracy goes almost to 1. And here I can already see the loss went almost down to 0.1, so it's like 0.11 something. And the accuracy, this is actually percentage, is almost 90%. I can also print now the graph as we did before. And here we see a much better curved and flattened training curve. And this, I would say, is exactly what we want. So I can do the same here now. I'm gonna upload an image in this piece of code. I'm gonna show it the network, and hopefully it will detect this one as a dog. And it's like 64% confident that this is a dog, even though it's kind of a hard image to detect, I would say. Let's do it again. I'm gonna run the code again. Let's upload another one. That's also, I think, quite interesting with the hand, but still it can identify this one as a dog. 75% confident on it. let's do it against a cat image and to double check. So yeah, seems to be, for example, here it's almost 100% sure that this one is a cat. So I think this is definitely a much better model or much better network we trained here compared to the one before. And even though we have less parameters in our in this model architecture. And for example, this one now you can easily run on your smartphone as well, because this model structure was also defined for this. So, for example, if you have an iPhone, it always does object detection when you hold it against something, and this model structure, for example, is running behind there. So this is exactly what is running on your smartphone. And so yeah, that's kind of a rush to these how these models are kind of transformed into code and how they are getting executed in Python on a Google Colab environment. And so we have MobileNet, and as I said, right, so we have different models. Again, I go back here. So these are really we just talked about this one in the first example. Turned out it's not the best structure for our model. Then we picked this one to the left here. But for example, here, this one on the bottom right, which is this interception model, is much bigger. And maybe it also performs quite well, but this is, for example, I mean, you can see already there are much more nodes and connections, so this has much more parameters in it. Maybe that's probably good for if you have a lot more classes and objects you want to detect. But coming back to this graph here, right? So the bias can sit into the model, right? So this is what this graph shows us. So you can never say that one model fits all task you would like to achieve. So here, when we plug in a model, we always have to check how good it performs on certain categories. And as the first one, for example, showed us, this was good enough to detect dogs, but it was not good enough to detect cats, for example. And there's always this kind of backward-forward process in training to identify it. But basically, with this kind of code here, with the MobileNet thing, that would be the thing that kind of runs behind our example, no? Where is it? Where we are? Well, you know, the door to open it, and that would be then first of all, the technology that sits behind the hardware to make a decision if it lets, for example, cats in and dogs not. That would be the code, so to say. I would say with this, again, like you